Section 13.5, the chain rule for functions of multiple variables. All right, so just like with functions in a single variable, we have to chain on derivatives whenever we have functions within functions. We're going to have the same thing going on here, only with multivariable functions, they can get a little bit wild on us. So we have several different cases. Let's go ahead and start outlining those. So the chain rule for one independent variable. Okay, so what we mean by having one independent variable is that both x and y are functions of a parameter t. So let's just outline this here. Let w be equal to f of x, y, where f is differentiable. If x is equal to g of t and y is equal to g of t, I'm sorry, g of t, h of t, yeah, doesn't have to be the same function for x and y, where g and h are both differentiable, then w is differentiable, and we get the derivative of w with respect to t is equal to the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. Okay, so that's the situation where x and t are both functions of a single variable. So now let's look at the chain rule for two variables. Two independent variables. Okay, so same thing except different. So we have w as a function of x and y, okay, where f is differentiable. Okay, so if x is equal to g of st and y is equal to h of st, such that all the first partials exist, such that all first partials exist for g and h, okay, then we have the partial derivatives of w exist. So the partial w with respect to s and the partial of w with respect to t exist, and they're given by the following. The partial of w with respect to s is equal to the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y, not w again, y, times the partial of y with respect to s. Okay, so I know that those partial symbols kind of look like 2's. I am trying to make them look like backwards 6's. That's how they look to me in the book anyway. But we read those as partials, right? And we're dealing with derivatives, so they are partials. Okay. And the partial with respect to t is equal to the partial of w with respect to x times the partial of x with respect to t plus the partial of w with respect to y times the partial of y with respect to t. So I'm going to put a box around those. Okay, so really the only difference in these two cases is that one of them only has the one variable t, so there's no partial there, right? It's dy dt or dx dt. Done. Here, though, we have to make that choice. Do I want dx with respect to s? Do I want it with respect to t? So anytime we have multiple variables, we're dealing with partial derivatives. So really these two things are exactly the same. The only difference is on one of them we have partials because we have s and t. So let's do a couple of examples and then we'll talk about implicit differentiation, which is everybody's favorite, right? Okay, so let's do some examples here. So example. Suppose I have w equal to x squared y minus y squared, where x is equal to sine of t and y is equal to e to the t. Let's find dw dt when t is equal to 0. Okay, so this is clearly a first case scenario because x is simply a function of t and y is a function of t. So there's only one independent variable. Okay, so the partial, no, not the partial. Dun, dun, dun. It's not partial, it's just d. So dw dt is going to be equal to the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. Okie doke. So let's see here. The partial of w with respect to x, that is going to be equal to 2xy. And then dx dt, the derivative, well, I'll just write it up here. Let's do another color, that way it stands out. Dx dt is cosine of t, and dy dt is just e to the t. Okay, there it is up there. Okay, so then dx dt is cosine of t plus the partial of w with respect to y is going to be x squared minus 2y times the partial of y with respect to t, or the derivative of y with respect to t is e to the t. Okay, so that's 2xy cosine of t plus x squared minus 2y times e to the t. Good. Now we're looking for this whenever t is equal to 0. So when t is equal to 0, what is x? What is y? Right? So let's see, for t equal to 0, that implies that x is equal to sine of 0, which is 0, and y is equal to e to the 0, which is 1. Okay, so then what we have now is that this is equal to 2 times 0 times 1 times cosine of 0 plus 0 squared minus 2 times 1 times e to the 0. Okay, so the first term zeroes out, and we are left with what appears to be negative 2. So negative 2 times 1, right? E to the 0 is 1. So then what we have found is that dw dt is equal to negative 2. Okay, now we could have found that by plugging in x and y, getting an expression of w in just t, and then finding our derivative in that way. So to show you what I mean, so let's see here. We could plug in x and y to get w as a function of t. Okay, so that would have been w equal to sine squared of t times y, which was e to the t, minus y squared, which is e to the 2t. Okay, so then we're going to have to, so dw dt, we're going to have to do a product rule for the first one, so that's going to be 2 sine t cosine of t times e to the t plus sine squared t e to the t minus 2e to the 2t. All right, and we want to know what is this when t is equal to 0. So when t is equal to 0, that would be 2 times sine of 0 cosine of 0 e to the 0 plus sine squared of 0 e to the 0 minus 2e to the 0. So that, of course, goes to 0. That goes to 0, leaving us with negative 2 times 1. So we get the same thing either way. The difference is sometimes it'll be easier to do it one way as opposed to doing it the other way. All right, so let's do another example. Suppose we have w equal to 2xy, where x is equal to s squared plus t squared, and y is equal to s over t. Find the partial of w with respect to s and the partial of w with respect to t. So find partial w with respect to s and the partial of w with respect to t. Okay, so the partial of w with respect to s, that's going to be the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s. So I need to know what all of these are. So I'm going to come over here and just kind of write them down over here on the side. So the partial of x with respect to s, so x sub s, that's going to be equal to 2s. The partial of x with respect to t is 2t. Partial of y with respect to s is 1 over t. The partial of y with respect to t is going to be equal to negative s over t squared. Okay. The partial of w with respect to x is 2y. The partial of w with respect to y is 2x. So now we have all of those. Those were very easy to find, and now we just plug them into the correct spot. Okay, so this is going to be equal to, go back to another color. This is going to be equal to 2y times 2s plus 2x times 1 over t. All right, but we don't want to leave this in terms of x's and y's. We want it all to go to s's and t's. So this is going to be equal to 2 times s over t times 2s plus 2 times s squared plus t squared times 1 over t. And we can simplify that just a little bit if we want. So that's going to be 4s squared over t plus 2s squared plus 2t squared over t, which will simplify to 6s squared plus 2t squared over t. Box around that. Okay, so now let's find the partial of w with respect to t. So I'm going to go ahead and come off to the side here so I can still see these. We have the partial of w with respect to t. So again, the partial is, it really to me looks like a backwards 6. Of course, it can get sloppy when we're writing it. It starts to look like 2's, that kind of thing. Please be aware that when you're seeing this in this context, that is not a 2, it is a partial. I've had people complain. So I just want to make sure we're all clear. We're all on the same page. All right, so this is going to be equal to the partial of w with respect to x, which is 2y, times the partial of x with respect to t, which is 2t, plus partial of w with respect to y is 2x, times the partial of y with respect to t is negative s over t squared. So that's going to be 2 times s over t times 2t, plus 2 times s squared plus t squared times negative s over t squared. Simplifying this gives me 4s plus 2s squared plus 2t squared times negative s over t squared. So that's going to be 4s plus, actually it'll be minus, won't it? Minus 2s cubed over t squared minus 2s. So altogether, that's 2s minus 2s cubed over t squared. All right, and there we have that one. So now on to implicit partial differentiation. Implicit. So let's write down the definition here, or the theorem, I should say. The theorem, if the equation capital F of xy is equal to 0, defines y implicitly, as a function, as a differentiable function, of x, then dy dx is equal to negative partial derivative of f with respect to x divided by the partial derivative of f with respect to y. And of course, because that partial is in the denominator, the partial derivative of f with respect to y, xy, is not equal to 0. Okay, all right, so there's that. If, let's go to 3 dimensions, capital F of x, y, z is equal to 0 defines defines z implicitly as a differentiable function of x and y, then we get the partial of z with respect to x is equal to negative f sub x of xyz divided by f sub z of xyz, and the partial derivative of z with respect to y is equal to negative f sub y of xyz divided by f sub z of xyz. And of course, the f sub z here cannot be equal to 0. So I'll just come over here to the side. Right, because it's the denominator, it cannot be equal to 0. Okay, so this is our implicit differentiation here. So we have this one for 2, and we have this one for 3 variables. All right, so let's go ahead and do an example here. So suppose I give you this equation, y cubed plus y squared minus 5y minus x squared plus 4 is equal to 0. And I say find dy dx. Okay, we begin by making sure that our entire equation is on one side with 0 on the other, so that we can say let f of xy, which is 0, be equal to y cubed plus y squared minus 5y minus x squared plus 4. Then we can find our partials. So f with respect to x is going to be equal to negative 2x, and f with respect to y, the partial of f with respect to y, is going to be 3y squared plus 2y minus 5. All right, then by our theorem, dx dy dx, sorry folks, dy, nope, still looks terrible, dy dx is equal to the opposite of, okay? So it's going to be f sub x divided by f sub y. So that's negative 2x divided by 3y squared plus 2y minus 5, which is 2x over 3y squared plus 2y minus 5. And there it is. All right, so let's go ahead and do another example. Let's go to 3 dimensions now. So we're going to find the partial of z with respect to x and the partial of z with respect to y, given 3x squared z minus x squared y squared plus 2z cubed plus 3yz is equal to 5. Okay, so we want to get everything on one side equal to 0. So 3x squared z minus x squared y squared plus 2z squared plus 3yz is, minus 5 is equal to 0. So that's going to be our f of xyz. Okay, so f with respect to x, the partial of f with respect to x is going to be 6xz minus 2xy squared. Okay, so those are the only terms containing an x. Everything else goes to 0. Fy, so the partial derivative of f with respect to y is going to be negative 2x squared y plus 3z. And then the partial with respect to z is going to be equal to, let's see here, 3x squared plus 4z plus 3y. Okay, so then our partial of z with respect to x is negative f sub x over f sub z. So that's going to be 6xz minus 2xy squared divided by 3x squared plus 4z plus 3y. And we can distribute that negative to get 2xy squared minus 6xz divided by 3x squared plus 4z plus 3y. Okay, and then the partial of z with respect to y is going to be equal to, where is that partial of y? There it is. Negative 2x squared, forgot the negative in front. Got to get that negative in front. Make space. Negative, there we go, negative 2x squared y plus 3z divided by 3x squared plus 4z plus 3y, which we can distribute the negative to get 2x squared y minus 3z, that's a 3, divided by 3x squared plus 4z plus 3y. Okay, so there we have it. So that's all I have for this video. If you have any questions, as always, please let me know.